Question 5. Hydrocarbon molecule contains covalent bonds. Part A. Define covalent bonds. So we know that covalent bond, it must be one pair of electrons between the nucleus. So let's say there is a chlorine molecules, and we know that between chlorine atoms there is one covalent bond, and this covalent bond, there are two electrons in there, and these two electrons must attracted by something. So the one or the species or the particles that attract these bonding electrons will be the nucleus. Okay, it's better to use this diagram to explain. So let's say this is the pair of electrons, the bonding pair in covalent bond. Because the electrons is negative charge, so it will attracted by the nucleus, which is positive charge. And the nature of this attraction is electrostatic, because it's attractions between the positive particles and negative particles. And this is why the covalent bond is quite strong and hard to break sometimes. Okay, because it's an electrostatic attraction. Okay, if you understand this, then the definitions seems like quite easy now. So the covalent bond is what? Is the electrostatic attraction between the nuclei of two atoms, and the shared pair of electron, means the bonding pair here. Part B. A CC double bond in alkene is made from a sigma bond and a pi bond. Means in the CC double bond is going to have one sigma bond and one pi bond. Okay, part 1. Identify the hybridization of carbon atoms in the CC double bond in an alkene. So first, you need to know the general structure of the alkene. So this is the structure of the alkene, how it looks like. And from this drawing, we know that each of these carbon, it will form 3 sigma bond. 1, 2, 3. This carbon also has 3 sigma bond. 1, 2, 3. So since it's formed 3 sigma bond, so we know that the hybridization of the carbon, it must be sp2. So because it needs the 3 unpaired electrons in the hybrid orbitals to undergo the ends-on overlap or the heads-on overlap to form the sigma bond. And the pi bond is formed from these unpaired electrons in the p orbital. So means each of these carbon, they will undergo sp2 hybridization, and it will form 3 sigma bond and 1 pi bond for each of these carbon. Again, the 3 unpaired electron in these hybrid orbitals will use to form the 3 sigma bond, and 1 unpaired electron in the unhybridized these orbitals, the p orbitals, to form the pi bond. Okay, this one form pi bond, this one form the 3 sigma bond. So therefore, we know that the hybridization of the carbon in these CC double bonds must be sp2. Okay, part 2. Draw label diagram to show in terms of orbital overlap, how the sigma bond and pi bonds are made in the CC double bond. So means you need to draw the overlapping. So how the orbital overlap. So this part you no need to draw, this one, just to show you how it looks like. So let's say now we have the 2 hybrid orbitals. So means one of these, only one of these orbital, these hybrid orbitals, okay, which look like this. 1 small loops and 1 larger loop. This one is 1 hybrid orbital, and it will overlap with another hybrid orbitals from another carbon. So these hybrid orbitals is from one carbon. This hybrid orbitals is from another carbon. And these two hybrid orbitals will undergo ends-on overlap or head-on overlap like this to form this sigma bond, right? So this is how the sigma bonds looks like after overlap. At least you need to draw this part. How is overlap? Means the two hybrid orbitals undergo end-on overlap, something like this. The larger loops will overlap, the smaller loops will not. Right, so this is what you need to draw. So how to form the pi bond? Pi bond is because of these p orbitals, the unhybridized p orbitals. So let's say this is the p orbitals from the one carbon, and this is another p orbitals from the other's carbon. So the two orbitals, or these two p orbital, will undergo sideways overlap, side by side. So this is the overlap that happened, this part and this part. So what you need to draw is this one, sideways overlap. So how is overlap? Right, so the p orbitals undergo sideways overlap, and it will form this pi bond. Actually, this is a nuclei. Nuclei is here. Nuclei is here. And this is the pi bonds that form. So it will be above and below the nuclei. If you want to draw this part also can. So this is how the orbitals overlap looks like. The sigma bond and the pi bond. Part C. In the electrophilic reaction involving alkenes, the pi bonds of the CC double bond is broken. Whenever there is electrophilic reactions, the one that always break is the pi bond. Means in the CC double bond, the bonds that will break is always pi bond, not sigma bond. Why? Very easy and very simple. Why pi bond is always the one that break before the sigma bond? Because the pi bond is weaker. So why the pi bond is weaker? Then you need to explain in the part 1. So suggest one difference between the sigma bond and the pi bonds that explain why pi bond always the one that broken in the electrophilic addition. Okay. Let's use back the diagram just now. After overlapping, this is the sigma bond. Actually, this one is closer to the nuclei. And for this pi bond, after it undergoes sideways, actually the electrons is further away from the nucleus compared to the sigma bond. That's why this one is always weaker, I mean the pi bond, and the sigma bond is stronger than the pi bond. That's the reason. Okay, so this is the answer, right? The pair of electrons in the pi bond are further away from nuclei. Therefore, the attraction is weaker. Part 2. This is about mechanism. You need to show the mechanisms for the electrophilic addition of hydrogen bromide to this 2-methylpropene, this one, to produce major organic product. If it's a major organic products, then you need to follow the Markovnikov rules. So let's say now we have these 2-methylpropene and the HBr that given. So first you need to draw the arrows. So you need to draw the arrows from the CC double bond, must form this CC double bond, and point to the hydrogen. Okay, why is point to this hydrogen? Because hydrogen is partial positive and the bromine is partial negative. HBr is a polar molecule, right? So because the CC double bond is electron rich, so it will try to donate its electrons to the partial positive side of the HBr, right, this molecule. And another arrow you need to draw is because there will be a new bonds formed between these 2-methylpropene with the HBr, then the O bonds need to break, the HBr bond need to break. So you need to draw one arrow from HBr, from this bonding, point to the bromine. And these two electrons will move or will go to the bromine, and eventually it will form bromate. Okay, if follow Markovnikov rules, the carbon with more hydrogens will get the hydrogen. Means this carbon has 2 hydrogen, so this hydrogen will form bond with this carbon. This is a Markovnikov rules, right? Because it will form the more stable carbocation. This is a tertiary carbocation, right? Okay, so after this step, these arrows and this dipole, the next step we need to do is to draw the correct intermediate. So draw the new bonding between this C and the hydrogen, and the other carbon here, this carbon is electron deficient, because just now the pair of electrons is no more. Now this carbon is lack of electrons, so you put a positive charge there. So this intermediate is a carbocation, and therefore this carbocation will attack by the bromide. Okay, the bromide here is formed from this part. So the bromide, you must put the negative charge and one lone pair. Draw one arrow from this lone pair, point to this carbon with charge positive. Must point to this carbon. Okay, after that, you just draw the products. Okay, which is the 2-bromo 2-methylpropane. Let's say this is the main chain. This is the main chain, propane. So this is second carbon. Second carbon has bromine and methyl. So therefore the name is 2-bromo 2-methylpropane. Okay, that's all. Thank you.